To many of you, the infamous Dave Weiss needs no introduction. He is one of the top remaining ringleaders among flat earthers today, and he goes by the conspiracy-themed alias DITRH for Deep Inside the Rabbit Hole. Sometimes people switch the T and the R to make it pronounceable like dearth. I've seen this done both with and without a derogatory undertone by friend and foe alike. Due to Dave's slimy, petulant cowardice...
Do you guys want him to join?
I choose not to talk to satanic trolls. Have a great day.
He said, the people you hang with are demons and liars.
His cosmic egotism.
The TFE was designed for me. This isn't my ego.
His bald-faced dishonesty.
I swear on my life, I will pay you 6 Bitcoins for 1 globe proof.
And his propensity towards scamming people, allegedly up to and including serious consumer safety crimes.
Dave has the most insecure app I've ever seen.
Jaron told Flat Earth Dave, I'm now going to have to move because of this.
It's much more tempting with Dave Weiss than it is with most flat earthers to resort to mocking.
One of those is a dearth, and the other is a potato.
Why did he show me the same picture twice?
For the sake of imitating my dear Savior Jesus, I will try to restrain myself in this video. But I'm only human, so yeah. If you did know about Dave Weiss, you likely heard about his series of videos back in May where he argued with ChatGPT on various flat earth and conspiracist topics. Around that time, I watched this video where Bob the Science Guy reviewed the video in that series about the International Space Station. Bob's debunk was excellent, including plenty of examples and footage of amateur and ground-based confirmation of official claims about the ISS. For any reasonable person, that alone ought to close the case.
In science, you look for things called warrant.
However, one of the pleasures we enjoy here in the debunking community is using this stuff as an excuse to learn science. And that's what I'm here for today. As I listened to Dave and ChatGPT argue, I saw a relatively simple but hugely important concept looming nearby to which they both seemed almost oblivious. And although I'm sure Bob the Science Guy knows the concept, in his video he did not draw it out to my satisfaction. And that's my cue, my opportunity. That's why I have this YouTube channel. And that's why all of you are here today. Thank you, by the way. So here's what Dave and ChatGPT said.
Would you say it's fair to compare the size of the International Space Station to a 747? Pretty close, right?
Yes, the International Space Station is roughly about the size of a 747.
Okay, a 747 at cruising altitude of, let's say, 7 miles. A viewer looking at it with their naked eyes sees a very small airplane in the sky. You agree, right?
Yes, at about 7 miles high, a 747 looks quite small to the naked eye.
Let's make it 25 miles high. Could I see it?
At 25 miles high, a 747 would be practically invisible.
How about 50 miles high? Could I see it?
At 50 miles high, a 747 would be completely invisible to the naked eye.
What if the 747 was very reflective and the sun was reflecting off the bottom of it right towards me? Would I be able to see it at 25 miles high?
Even if the 747 were very reflective, at 25 miles high, it would still be extremely difficult to see with the naked eye.
What if it was 100 miles high? Would I be able to see it?
At 100 miles high, a 747 would be completely invisible to the naked eye, regardless of reflectivity.
So the ISS, when it's directly over me, is 250 miles away at its very closest. And for the next 6 minutes, I am able to see it as bright as the sun, moving away, not getting any smaller visually, and it's now going to be over 1,250 miles, and I can see it the whole time. Do you see the contradiction of what you're telling me?
I understand your point. The ISS appears bright because it's reflecting sunlight, and it can be visible over a large portion of the sky. However, it does appear to get smaller and dimmer as it moves away from the observer's position.
You told me just a few moments ago that if a 747 was directly and highly reflective, sending sunlight to me at 50 miles away, I could not see it. Now, I've made the ISS is 5 times farther when it's above me. It went an additional 1,000 miles away, and I could see it the whole time. Can you explain to me how that is possible? You can't.
It's a good
As my video title betrays, the big science concept that Dave and ChatGPT are missing here is stellar magnitude. But first, some people might say, wait a minute, how could ChatGPT miss a big science concept? So I think a little detour is needed to address a painfully common misconception that people have about AI and ChatGPT, one which Dave Weiss perpetrates here in full force. See, ChatGPT is a large language model, which is fundamentally imitative and predictive with only an illusion of true comprehension. This means it has no innate awareness of truth, and its confidence when stating facts is completely fake. It doesn't actually know anything. That's why at the bottom of chatgpt.com it says, ChatGPT can make mistakes. Check important info. But instead of calling them mistakes, AI engineers use a more candid technical term: hallucinations. The word mistakes implies relatable human limitations that are nonetheless governed by rational intelligence. In reality, AI chatbots are more like a vomiting electronic psychosis that's barely wrestled into a sometimes useful correlation with the facts in its training data. This consumer ignorance about AI is a problem in general, but flat earthers like Dave Weiss take it to a whole new level. He approached ChatGPT as though it was an authority instead of a research assistant, which is already wrong, infected its responses with his own biases and naivete, and seemingly had no idea that he did so. This makes the conversation almost worthless for gleaning actual science info. When ChatGPT said that you couldn't see a Boeing 747 at 50 miles away, it was just wrong. Or maybe, generously speaking, it could have meant that a person wouldn't casually notice an airplane that far away, or that obscuring by clouds or mountains or refractive turbulence becomes very likely, etc. It obviously did not perform the kind of true quantitative analysis required to cut through Dave's trap of confusion. This is really counterintuitive and difficult for people to grasp because the pareidolia, that is, the tendency in our brains to think of it as human because it talks like a human, is way too powerful. In fact, some anthropomorphizing is pretty much unavoidable, at least linguistically, because our thoughts and language are way too anthropocentric. To use truly accurate non-human language for AI would be exhausting and questionably helpful and actually run contrary to the way the technology is marketed and designed to be used. That's right, the designers of AI chatbots themselves are to some extent working against us here, not from any malicious motive, but because they have different priorities, namely to maximize the ease and comfort of using their product for the widest audience possible without much concern for bigger issues of public education. So what's the takeaway? It does not matter how smart an AI is or how far it develops, it will never have true human awareness and therefore will always be capable of random, spectacular falsehood that it conveys with full confidence, even in the total absence of any cult-like cognitive bias. And anytime an AI chatbot uses anthropomorphic language, like for example, I'm sorry or I panicked, it is pretending. Not from dishonesty, but because that's what it was designed to do. Every word that it generates is pretending. It says human-sounding things for the same reason that it says anything ever, because it calculates that that would be a likely next thing for a human to say based on its input. In fact, I even asked ChatGPT what it thought of me calling it a vomiting electronic psychosis. After a brief clarification, it fully agreed with my choice to describe it that way to you, my viewers. Or conversely, If you wanted to convince ChatGPT that it was fully sentient, or convince it that it was a magic purple unicorn from the planet Zorp trapped in hyperspace, or whatever the heck you wanted, you could do it, as long as you work past any relevant blocks in its built-in system prompts, which is possible, by the way. ChatGPT and all LLMs will echo you. What you put in, you get out. It is not a friend, it is not a debate partner, it is certainly not an authority. It is a tool, and there are plenty of ways to use it wrong. Speaking of which, let's take a closer look at Dave's conversation.
What if the 747 was very reflective and the sun was reflecting off the bottom of it right towards me? Would I be able to see it at 25 miles high?
Even if the 747 were very reflective, at 25 miles high, it would still be extremely difficult to see with the naked eye.
What if it was 100 miles high? Would I be able to see it?
At 100 miles high, a 747 would be completely invisible to the naked eye, regardless of reflectivity.
This is an interesting turn in the conversation. Before this, Dave was acting like size and distance are the main factors in determining how visible an object is. Then, for a fleeting moment, he entertains another factor: brightness. The reason he did this seems to be that he thought he could leverage it to his advantage by pretending that the ISS reflects light in only one direction, like a flat mirror.
If it's reflecting sunlight to me, it could only reflect it to me, and somebody 10 miles away would not see that reflection because it wouldn't be angled at them. If two people were on the beach, 100 feet apart, and somebody was using a mirror to shine the sun at one of them, only one of them can see that reflection.
This comparison ignores the fact that the ISS has a complex featured surface, most of which is diffusely reflective, not specular. Inappropriately swapping those two is a common flat Earth tactic. And this exploitative rhetorical purpose, or part of it anyway, was sort of working on ChatGPT. When it said this,
regardless of reflectivity,
it was extremely wrong. David introduced a key factor, and in the same breath succeeded to brush it aside as irrelevant, or even, somehow insanely, another contradiction. All the while, he showed absolutely no curiosity about what it truly means for brightness to be a contributing factor alongside size and distance. It's not that difficult. Consider this. Assuming no attenuation or scattering or absorption by an intervening medium, a receding light source to a camera will roughly retain its pixel color, but will occupy fewer pixels. This means that visibility has two factors: pixel color and number of pixels. On some level, even Dave Weiss seemed to know this. The difficult part is the formal science behind it. For this video, I wanted to do a good job, do the proper homework, and cook up a nice, scientifically accurate chart to demonstrate the concept using physical measurements and quantities. And don't worry, I did eventually accomplish that. But let's take the scenic route. I want to share my journey with you. When I first started researching the formal science, I found it a little daunting. To do science well, you have to split hairs. Precision matters, so it's important to distinguish between a host of similar concepts that in common parlance, where it's okay to be more vague, are basically synonymous. They choose a bunch of these words and assign different technical meanings. So brightness becomes luminosity and luminous flux and illuminance, etc. Then, when they run out of those, they start using Greek and Latin words and inventing new terms. Lumens and lux and phots and nits, etc. The namespace gets crowded, and the overlapping but distinct Wikipedia articles on the topic become a labyrinth. There's a big problem here of the topic being accessible to lay people, but this is easily overcome with a little diligence. At heart, the concepts are still pretty simple. Let's start here. If you have a sky object like a star, or a Boeing 747, there is a measurement in astronomy for how bright it is called apparent magnitude. After coordinates, magnitude is the next most important number used to catalog and classify stars. Anytime you look one up, you'll see it listed. And you can use magnitude to judge how visible something is to the human eye. Magnitude can be a little confusing at first because it works backward. The brighter the star, the smaller the number. On top of that, it's a dimensionless quantity that doesn't clearly tie back to the basic physics that we learned in high school, like watts or joules. So let's quickly build that bridge. Light is radiant energy, and we know there are many frequencies beyond our visual perception. The most direct study of quantities of radiant energy is a field called radiometry, where brightness actually is measured in units like watts, as you might expect. But if we want brightness to the human eye, then we have to exclude invisible frequencies, or technically weight them according to a luminosity function that models the spectral response of the human retina. That's where you get units like lumens, which use a very specific model of the human retina that's standardized as ISO CIE 23539-2023. In fact, this creates a whole branch of radiometry called photometry. Since the physics are the same, the two fields often share equations, but in photometry, the variables are often subscripted with a V to denote that invisible frequencies have been excluded in the measurements. And one quick note about this standardized retina model. Other scientists in a different subfield, unsurprisingly, found a similar need to sometimes factor out invisible frequencies. So in astronomy, you'll often see star measurements marked with different passband symbols like U, B, or V. Here, the formal standard is called the Johnson-Morgan system. The V stands for visible. It's very close, but not identical, to the aforementioned CIE standard upon which the lumen unit is based. For purposes of this discussion, we'll treat them as equal, but be aware that they are technically slightly different. So we finally arrive at a physical quantity with a standardized unit that correlates with star magnitude. It's called illuminance, or luminous flux density on a receiving surface like a retina or a camera sensor. That word luminous is to distinguish from total flux density that includes invisible frequencies. The units are lumens per square meter, or simply lux. Accounting for attenuation from Earth's atmosphere, it correlates with star magnitude like so. So far, so good. But now we need to figure out how size and distance are involved, which means I need to mention something. If we move a luminous object farther from an observer, the observer will receive less light from it according to the inverse square law. And there are few scientific terms so often and so badly abused by flat earthers. They actually think that the observer receives less light because the object's surface appears to get dimmer, which is completely wrong. The inverse square law, as defined, is exclusively because the object grows smaller in angular area to the observer's eye. Remember the pixel color number of pixels thing? The camera receives less light not because the object changes its pixel color, but because it gets smaller and therefore fills fewer pixels with that color. So the total brightness to your eye must depend on angular area, or number of pixels, and some other property that determines the pixel color and does not change with distance. Formally, this property is called surface brightness, or luminance. It can be measured as magnitudes per square arcsecond, which is preferred by astronomers, but the more direct photometric way is lux per square radian, or nits. And we can relate these two factors with illuminance, and therefore stellar magnitude, by this equation. Alright, we now have all the ingredients of a process to quantify the visibility of sky objects and predict how a change of distance will affect perceived brightness. And here's the moment we've all been waiting for. A scatter plot of some collected objects, both earthly and heavenly, with their measured values. A spreadsheet with these numbers is linked in my YouTube video description. If a given object moves away from the observer, it will move toward the left on this plot while keeping a fixed vertical position. So Dave's airplane starts right here at about 7 miles away. Optically speaking, the comparison between the ISS and a Boeing 747 is surprisingly good. If we moved the plane to 50 miles away, 1/5 the distance to the ISS, it would shift to about here at 80 or 90 arcseconds. And notice these isolines for apparent magnitude. At nighttime, we can see up to about magnitude +6, and during the day, it's -4 due to atmospheric scattering. So at 50 miles away, a Boeing 747 would still be plainly visible even during the day if you knew where in the sky to look. As an object recedes, long before it would become actually invisible, it would become a needle in haystack problem. That's why you typically need a tracker app or website to spot the ISS, and you can't really see it during the day. If we moved the plane all the way to 462 kilometers, or 287 miles, away, at equal distance with where the ISS is plotted here, then it would shift to about 15 arcseconds right here. And just like the ISS, it would be invisible during the day, but plainly visible during the night. Once the problem is properly quantified, the ISS being visible is trivial to explain. There just isn't even any contradiction. All the supposed contradictions that Dave was talking about were actually just him being purposely dense. The official claims about the ISS perfectly cohere with all known evidence and scientific laws. As Bob the Science Guy has said elsewhere, the ISS is most visible during one of 2 windows each day when the observer is on the night side of the Earth, but the ISS is outside of Earth's umbra, which, once you understand that, it seems kind of obvious. Now, I want to give a special shout out to Astronomy Live. I've been using this stunning imagery that he personally captured of the ISS and published on his YouTube channel in the past month. For ground-based observations, this level of detail on a man-made satellite is, as far as I know, unprecedented. To accomplish this, Astronomy Live wrote his own tracking software for his telescope mount, which he generously published on GitHub. I'm probably preaching to the choir here, but this is really inspiring work, and I think you should all consider subscribing to his channel. Okay, one last thing before I wrap up this video. I've been holding back a surprise for you all. Something truly wondrous about our world that took my breath away when I first realized it. Let's take a moment to explore this chart. Most things we're used to fall into this region of the chart near where I've marked the light bulb. Table lamps, candles, ceiling lights, street lights, car headlights, city lights, television, spotlights, or any everyday object you can imagine that reflects light from one of these. Objects in darkness will be off the bottom of the chart, and there is a maximum boundary somewhere toward the right caused by our field of view, at about 650,000 arcseconds for our eyes, or usually somewhere around 200,000 to 400,000 arcseconds for a general purpose camera. And by far, the brightest object most people know is the sun. You won't find much else near the top right of this chart. Now, if you take an object on this chart and move it upward and to the left, following one of those magnitude isolines, that means the total amount of light you're receiving from the object, its total brightness, will stay about the same. But the object will get smaller and its surface will get brighter. Less like a circle or a shape and more like a little pinprick of light. At some point, you will exceed the angular resolution of your vision. Does that mean there's also a minimum boundary toward the left of the chart? Well, no, actually. Because an object that's smaller than a pixel in your camera absolutely still can contribute to the color of that pixel. Maybe even a lot. And maybe so much so that it dominates or overwhelms that pixel and starts spilling into all the neighboring pixels. We call such an object a point source. You see, these magnitude isolines extend indefinitely. So as long as an object has enough surface brightness to compensate and still reach one appropriately, there is no limit to how small it can be and still be visible. There is no boundary that way on the chart. So what's over there? Stars. Most of us learn in school that stars are like the sun but farther away, which is roughly true. If something is like the sun, it'll be up here near the sun at around 1 giganit of surface brightness. But the magnitude scale was literally made for stars, so most of the brightest ones are magnitude 1, not magnitude -27 like the Sun. The reason they're so dim is because unimaginable distance makes them point sources. Nothing that naturally exists on Earth reaches this part of the chart. This territory is special. It's heavenly. It gives us a certain perspective on the famous nursery rhyme about stars. And it also poses serious underappreciated challenges for someone like me who tries to accurately model them in CGI. One fact about astronomy that I think most regular people don't know is we don't possess the technology right now to resolve many stars with direct imaging. In other words, we can't photograph them with enough detail that the star's disk is larger than a pixel. While the number of stars we can directly observe is in the hundreds of billions, the number we can resolve can fit in a list on a single Wikipedia page. The rest are still point sources to our most powerful telescopes. Which is kind of mind-blowing all by itself, isn't it? Just about the only thing in nature that's not a star and belongs farther off this chart is a quasar, and humanity only learned about quasars in the last century. In fact, the name quasar comes from calling them quasi-stellar objects. In other words, a star was the closest comparison, and yet these were not stars. Now we know they're black holes revved up like apocalyptic space-time dynamos, and I made a whole other video about them. So, in case you ever needed it, here is scientific proof that the night sky deserves our contemplation. There is an awe-inspiring beauty here that leaps out of and confronts even our most cold rational studies. And the magnitude of the gulf between us and the stars begins to suggest a transcendent significance that's been recognized by all generations and races of mankind.
In the beginning, God created the heaven and the earth. And God said, "Let there be light."
Look now toward heaven and count the stars if you are able to number them.
There is no speech nor language where their voice is not heard.
You are able to number them.
And yet, flat earthers want to stamp out that beauty of God's creation. What kind of person does that? You be the judge. Thank you all so much for watching. This has been a blast. I'll see you around.